Hello everyone, this is Chris. I've got an algorithms question for us today. Let's dive right in. Suppose you have a list of birth years and a list of death years for a certain population. Can you determine the year at which the population was the greatest? You don't know what the maximum or minimum years for birth or death are, so the domain could be 100 years or 10 billion years. You don't know. It would take too long to go year by year, so we'll use a heap instead. Now, how can we use a heap to do this? This is a pretty classic algorithms question, and so I wanted to actually look at how to implement it in Python so that we could implement it quickly after identifying it as this type of a question. So let's switch over here and let's look at heaps in Python and how we can quickly implement them. So first of all, the priority queue is a special kind of heap in which keys and values are stored together and they are ordered by the key. So the key value pairs in a heap, the minimum key value is always at the root. So when you pop an element from the priority queue, we recover the key and value for the element with the smallest key. And why in this case would we want priority queue? It's because the data that we are storing in the queue is whether the event was a birth or a death, but we need to store them ordered by their year. Okay, so I've got a little demo here for HeapQ, so we can go through that first in Python. So we're going to bring in random, that's just so that we can get random data into our heap. And then we import the HeapQ module, which is part of the standard Python library. So we will begin by creating a list, which we call heap. And you can see this list is going to be generated as random integers in a tuple. But for the sake of demonstration, let's remove the tuple and we will just make this a random integer. So this will just be 20 random integers, and we're going to print that out, and then we're going to create a heap, transform list into a heap in place in O length of x time, so that's in the length of the list, linear with respect to the list. And we're going to print out that heap, so it will reorder the elements. Might not be what we're expecting, but we can actually look at the order that they appear in the list structure. But when we pop them using heap.pop, you can see here, pop the smallest item off the heap, maintaining the heap invariant, which means that the heap will still maintain nodes, child nodes that are less than on the left and greater than on the right relative to their parent. Let's print this out to console and see what we get. So you can see the first output here, this is just a random list of integers, 20 integers. We turn it into a heap and you can see it sort of tends to weight smaller elements to the left, but not necessarily in sorted order. And that's because we just made it into a heap. We didn't sort them yet. To sort them, we have to pop them off the heap. So you can see they pop in order. And when you pop, they are actually removed from the heap. Okay, so now what if we wanted to store some data with that key? Let's do it in a tuple. So we'll just generate this. And this time they will generate from 20 to 29. So you can identify that data. Okay, so we'll generate a tuple, 20 tuples. The key is between 1 and 10, the value is between 20 and 29, and then we'll print out the same thing. Okay. You can see it's much more information for us to work with, but if you look at the heap, generally it's much more ordered by its first element. There is some ordering by the second element, but not as much. And why is that? Well, let's look. It's because the ordering is first by the first element, and second, it is ordered least to greatest by its second element. So basically that second element, the value, is the tiebreaker. So we can implement a priority queue in this way. Okay, let's apply the priority queue to the sample problem that we have. Okay, I've got it set up with random. That's just so we can create random birth years and death years. And I have imported HeapQ. Then I just set up two random lists. The first one from 1825 to 2023, and we have between 200 and 210 births. And then deaths from 1826 to 2023, we have between 190 and 200 deaths in this population. Now what we need to do is create event tuples, which will be a birth year with the number 1 to increase the population, and the death year with the number -1 to decrease the population. And then we'll convert that into a heap. So first we'll call this events. Well, let's do the births first. Excuse me. So year, comma, 1 for year in birth years. And then we'll combine that with year, -1 for year in death years. Okay, now that's our events, and then we can use HeapQ on events to turn it into a heap. And now we have a data structure we can work with. When we pop years, we will know the year and whether it was a birth or a death, and we will do this in order. So we need to start out. What's the current population? 0. What's the max population so far? 0. And which year has that max population? None. Great. Initializing all of our variables that we will be using to capture our data. And then we're going to loop through our events. And we'll loop by index. So for I in range events, so 1 index for each event. And now we'll have year and value will be equal to HeapQ.heap pop on the events. Okay, what does that do? Pop out the first event, get its value, and then we add its value to the current pop. If it's a death, it will subtract. If it is a birth, it will add. And then basically, if the current pop is greater than the max pop, then we'll let the current pop be the new max pop. And the max year will be the current year. Now, one thing, let's go back to the events really quick. The year of someone's death, they are alive. So we actually want to be subtracting 1 from our population the year after they die. We're not necessarily considering them all alive at the same time, just people who are alive during that year. So even if someone was born after somebody died, they were both alive during the year, even though they were never alive at the same time. Okay, so after we loop through our events, we calculate a maximum pop and a maximum year. All we need to do is then print out the year and the population in that year. And then what we will do is run this and just check our syntax errors really quick. Okay, so that ran quite nicely, and what this is telling us in this random data set, we have 2014 with 17 people having lived in 2014. If we run our data set a little more, 2005, okay, 1947, interesting. We have essentially solved it. Essentially our runtime is the time it takes to sort the elements, which is n log n, and that's as best as we're going to do. And our data structures are all linear in size. Okay, so just out of curiosity, I thought let me run this with a larger data set, 1900 to 2019 with 100,000 population. Let's make it a million and see how this goes. Alright, in 1941 we had 9,842 people alive. That's sort of interesting, but you can see how this algorithm is strong enough to handle even 2 million events in just a matter of a few seconds. If you were searching with brute force, this might not be possible on a standard sort of desktop computer. So there you have it. That's how we implement a heap queue in Python and a priority queue to answer this algorithm. Hope you enjoyed it, and hope you tune in next time. Thanks.